This video is an introduction to topology and rigorous math for calculus students. As long as you're familiar with the notion of a continuous function, we're going to prove that if n greater than 1, then Rn is not homeomorphic to R. What does homeomorphic mean? We'll explain that intuitively and rigorously in this video, and we're going to prove this property that higher dimensional Euclidean spaces like the plane, three-dimensional space, they are not essentially the same. They're fundamentally different from the number line. And that's an intuitive concept. It comes down to the notion of dimension. Okay, they have higher dimension, but actually proving they're not homeomorphic is quite a subtle and interesting statement. We're going to have to be precise about what homeomorphic means first of all. So what homeomorphic means is that essentially they have the same topological structure, which is to say they have the same idea of closeness, the same global shape. Okay, so I'm going to define what homeomorphism is to start off with. So we're going to think of Rn as a plane. Okay, we're going to imagine n equals 2, and we're going to have R, which is the number line. Okay, R is a number line. Now, a homeomorphism is the following. It is a function f from Rn to R that basically has three properties. Property 1 is that f is bijective. Okay, so f is bijective. Now, bijective basically means that it is one-to-one and onto. Okay, so one-to-one means that distinct inputs get mapped to distinct outputs. Okay, so you have x and y, they get mapped to different elements of R, so f of x and f of y. So if x is not equal to y, then f of x is not equal to f of y. Okay, so that's true. And the second property, onto, means that every output has an input that corresponds to it. Okay, so if we have some z here, let's say there's a z here, there is a w in R2 or Rn if you like, here I'm visualizing n is 2, that gets mapped to z. Okay, so f of w is equal to z. And basically you can think of the combination of these two as saying that every z in R, there is a unique w. So that's both one-to-one and onto, not multiple w's, a unique w, so that f of w is z. That's what it means for f to be bijective. And so that's not really topology yet. That's just a nice function that really corresponds, uniquely points of R to points of R. Topological structure is about closeness, so that's where we bring in continuity. So we want that f is continuous. That means that small changes in the input give rise to small changes in the output. And we also want f inverse to be continuous. Okay, so f inverse to be continuous means small changes in the output give rise to small changes in the input or correspond to small changes in the input. Okay, so that's saying that the notions of closeness matches up for both these spaces, and that's what it means rigorously for them to be topologically the same. Now, we feel they shouldn't be topologically the same, so we have to rigorously prove that we cannot have such a function. And what we're going to do is we're going to do it as follows. I'm going to capture the notion of dimension very precisely. Dimension is really a topological notion, okay, and how it plays out is going to be very important. So what we're going to do is we're going to look at the following interesting structure. So we're going to do a proof by contradiction. We're going to assume there is such a function with these properties, and we're going to get a contradiction. So we're going to think about what it means to be two-dimensional, okay, and we're going to think about this very creatively. Okay, this is a very creative idea. So we're going to cut out the origin from R2. I'm going to cut out the origin from R2, and notice something very interesting when we cut out the origin from R2 is that any 2 points in R2, suppose you have these 2 points, right? They could be connected in R2 by a straight line. If you delete the origin, they can still be connected in R2 by missing the origin. If we just perturb our path, okay, we move around like this, for example, we can miss the origin. So we can still say that R2 minus a point is connected. Okay, and that actually reflects the second dimension, because if we were only having one dimension to play with, if we delete, for example, R, if we delete a point from R, okay, R minus a point, let's say P, we cannot connect points that are on opposite sides of this one by a continuous path, right? We cannot go within this R minus P, this is P, we would have to cross P to connect points on opposite sides. But in R2 we can use the second dimension. Okay, so that's going to be a fundamental topological property, and we're going to understand why that is in our definition of homeomorphism. So let's now get into that proof. By the way, if you're enjoying this video so far, please don't forget to leave a like. It makes a huge difference for the channel, and I love helping people and helping to reach as many different people as possible to introduce them to advanced math in an accessible way. So let's now explain what the proof should be. So this is our proof, is assume there is a homeomorphism, and I'm going to actually just visualize R2. The same argument works in Rn. What I said is true in higher dimensions as well. If you delete one point, you're still connected. So what we're going to do is make precise this idea. So we have a function from R2 minus R, it's a homeomorphism. It's continuous, bijective, inverse is continuous. So we're going to see where we use these properties. Now what we're going to do is we're going to look at R2 minus 0, okay? Now, as I said, it's bijective, f is bijective, so points in R2 correspond to points in R uniquely, okay? So if we have R2 and we delete 0, we can think of f as a new bijection. We can maybe call it f prime if you like, because its domain is different. It's a bijection from R2 minus 0 to R minus f of 0. So basically what's happening is that 0 is the only point that corresponds to f of 0 because f is bijective. So you have a nice bijective function here, and it's again continuous, its inverse is continuous. You know, restrict continuous function to a smaller domain, it's still continuous. Small changes in input still correspond to small changes in output. Now we have used the bijectivity so far, and it's very important because, for example, if you take the plane and you just project everything onto the x coordinate, right? You just map x, y to x, right? This is a function from R2 to R. It is not a homeomorphism because it is not bijective. You know, a whole line, a whole vertical line of points in R2 are mapped to one point. So it's not one-to-one, and this is not a valid example of a homeomorphism. So we have to use the bijectivity, which we have done so far. Now we're going to capture the fact that in this space, R2 minus 0, it's connected. 2 points can be connected by a path. In this space, they cannot. And here's what we're going to do. Look at R minus f of 0. Okay, now think about f of 0 minus 1 and think about f of 0 plus 1. Okay, so we have those 2 points. Now we know we cannot connect them in R minus f of 0. We're going to have to make that precise though. Okay, but imagine those 2 points. Now imagine in R2 minus 0, you have 2 points, P1 and P2, right? So you have 2 points that say P1 and P2. We don't know where they are. I'm just labeling them. We don't know where they are. There could be any points. And we know that f of P1 is equal to f of 0 minus 1. We're choosing them this way, okay? We're choosing P1 and P2 because f is bijective. We can do that. And f of P2 is going to equal to f of 0 plus 1. Okay, so that's going to be our function. And we know that P1 and P2 can be joined by a continuous path in R2 minus 0. In other words, we can choose a path phi. So let's say phi is a continuous function from 0, 1 to R2 minus 0. Okay, so I'm writing this out very rigorously. I'm showing you rigorous math. Okay, we are not just satisfied. We have to really see how every condition is coming in. We're not just satisfied with the intuition. So we have a function 0, 1 to R2 minus 0 because intuition can be very fuzzy. You know, there are things like, you know, space filling curves. There are examples of curves that fill up the whole space. How can a one-dimensional continuous function fill up the whole space? There are examples of weird fractals, lots of counterintuitive stuff in math. So you have to be very precise. So we have a path from phi from 0, 1 to R2 minus 0, so that phi of 0 is equal to P1 and phi of 1 is equal to P2. That we know, okay? So that's an example, and I encourage you as an exercise, can you write it down explicitly in terms of P1 and P2? Say we give the x and y coordinates of P1, the x and y coordinates of P2. Can you explain, maybe split into cases to write down the continuous path that connects them? So it may not be the straight line path if they're opposite, but if they're opposite, you can write down a path very explicitly. That could be a fun challenge. So you have this continuous path, and now what we're going to do is we're going to observe that using a homeomorphism, right? The idea of homeomorphism is things are the same topologically. So here we have a continuous path. Continuity is basically what's preserved under homeomorphisms. So now that means that if we compose with our homeomorphism f, our alleged homeomorphism f of phi is now a function from 0, 1 to r minus f of 0. And now with this function, we know that f of phi of 0 is going to equal to, well, phi of 0 is P1, f of P1 is f of 0 minus 1. Okay, so this is f of 0 minus 1, and f of phi of 1 is going to equal to f of 0 plus 1, and that's already, you know, that's pretty cool, so we got that. So therefore, it's a continuous function from 0, 1 to r, right? R minus f of 0, 0, 1 to r, and we know that this value is less than f of 0, so I'm going to write it out like this. This value is less than f of 0, this value is greater than f of 0, right? And so intermediate value theorem, this is where our calculus comes in. Intermediate value theorem, IVT implies that there is a C inside 0, 1. Okay, there's a C inside the interval 0, 1, such that f of phi of C is equal to f of 0. But we know that f is bijective. That means that distinct points get mapped to distinct things under f. So if f of phi of c and f of 0 are the same, that means that phi of c is equal to 0. Okay, so I'm going to write that up there. And watch till the end for an intro to algebraic topology. I'm really showing you a lot of advanced stuff in one video, so I'm going to show that shortly. But that implies that phi of c is equal to 0. And that's a contradiction because phi was a continuous path connecting P1 and P2 in R2 minus 0. So it never touched 0 as we explained visually, and that's a contradiction. Notice that we did not use the inverse being continuous, and that may seem like a little bit of a different sort of condition. It's a very important condition in general. We did not use the fact the inverse is continuous, but we did use the continuity of f, and we did use that it was bijective. And we've shown that there cannot be a continuous bijective function from R2 to R. Okay, that's one way of looking at it. But, homeomorphism should be a symmetric relation. So, saying that two things are homeomorphic, you could also go the other way. So if we went the other way, if we said we have a continuous function from R to R2 and it's bijective, that could maybe be possible. That hasn't been ruled out. There we'd have to use the inverse being continuous to replicate this argument, which was based on the domain being R2 and the range being R. Okay, so we have to think about it in that way. And a very beautiful example of topology and dimensions is this video. But what happens in higher dimensions? What about R2 and R3? We've shown that Rn cannot be homeomorphic to R. I mean, prototype is R2. What about R2 and R3? Deleting a point from R2 and from R3, both would still be connected, right? So how do we think about that? I'll just show that to you briefly. So with R2 and R3, what happens is interesting. R2 and R3, deleting a point, they're still connected. But actually, topologically, they're still different in a fundamental way, and that requires creativity. So I want you to pause the video right now and drop a comment why you think these two shouldn't be homeomorphic, R2 and R3. What is special about R2 minus 0 that isn't true for R3 minus 0? This is a super creative idea. It's very, very hard to come up with, but I'll just show it to you right now, assuming you pause, just to think about it creatively. R2 minus 0, you can connect points in R2 minus 0. It is connected, but you cannot contract loops. This is the next dimensional analog. You cannot contract a circle to a point if the circle surrounds your puncture, your deleted point. Whereas in R3 minus 0, the extra dimension, even if I had a circle that surrounded my origin, I could contract it to a point by lifting it into the third dimension and then contracting. Just like I could connect two points opposite to each other by a path in R2 minus 0 by lifting into the second dimension, this idea of looking at loops being contracted is what's called the fundamental group. And it is the beginning of the subject of algebraic topology that captures the notion of higher dimensional holes. Now, I've got two fun video recommendations for you. You're going to love this to really help you digest very similar ideas in topology. The first one is, what if I delete R2, I delete Q2? Okay, so Q2 is all the points with rational coordinates in the plane. And that's like such a minefield. That's like so many different things are deleted. If you delete Q from R, you get something that has so many holes, all the irrational numbers. There's so many holes everywhere. Here also it looks there's so many holes, but actually it's connected. You can connect any 2 points by a path. What's the proof? Check it out. It's going to pop up on the screen here. And another fun video, it's all about the comb space. A very interesting space, an infinite comb, defined precisely. It is connected, but you cannot join 2 points by a path sometimes. It's not path connected. What does it mean to be connected but not path connected? That video is going to explain. It's an intro to topological ideas. Check it out. It's going to pop up on your screen.